molar specific heat. The molar specific heat of an ideal gas. Internal energy E internal. Let's first assume that our ideal gas is a monoatomic gas, which has individual atoms rather than molecules, such as helium, neon, or argon. Next, recall that internal energy is the energy associated with random motion of atoms and molecules. So let us assume that the internal energy E internal of our ideal gas is simply the sum of the translational kinetic energy of its atoms. Individual atoms do not have rotational kinetic energy and no potential energy involved because the distance between them is pretty far away. The average translational kinetic energy of a single atom depends only on the gas temperature T and is K average equal to 3 times half kT equals 3/2 kT. A sample of n moles of such a gas contains n Avogadro number atoms. The internal energy E internal of this sample is then E internal energy equal to this number, NA times A average. That is NNA times 2/3 kx. And we know that when NAK is constant R. So this E internal equal to 3/2 nRT. So E internal for monoatomic gas equal to 3/2 nRT. This is only for monoatomic. The internal energy of EM of an ideal gas is function of gas temperature only. It does not depend on any other variables like voltage, pressure. Molar specific heat at constant volume. This is a specific heat at constant volume. We look at this gas, okay, ideal gas. We lock the piston by a pin. So the gas cannot expand it or be compressed. Here we have a heat reservoir, you have a heat exchange. So we look at this one, the V is constant, this is P, this V is constant from initial state to the final state, okay? P changes, T changes, okay? We want to find the molar specific heat at constant volume. We know that's when at constant volume, the work done by the gas is 0 because dV is 0. And the Q, the Newton's first law, Q equal delta E plus W. W equals 0, so Q heat absorbed equal to delta E internal. Okay? And by definition, at constant volume, the QV equal to C delta T for the N. This is definition. Okay? Then we got this Q equal, so we get delta E equal to NCVT. And CV equal to 1/n delta E internal or delta T. This is molar specific heat at constant volume. And we know that the E internal equal to 3/2 nRT for monoatomic gas. Okay? Atomic. And then we put this one delta, we get a delta E equal to 3/2 nR delta T, and this is the C equal to 3/2 R. This CV is for monatomic gas. We now generalize above equation for the internal energy of any ideal gas by substitute CV for 3R over 2. Then we get E internal equal to N CVT. This is generalized for all kind of stuff. Okay. Any ideal gas. Okay. This equation applies not only to an ideal monoatomic gas, but also diatomic and polyatomic ideal gas, provided the appropriate value of CV is used. CV is changed. CV for diatomic is one value. For polyatomic is another value. It's from different from 2/3 R. We see that the internal energy depends on the temperature of the gas, but not on its pressure or density. So we get a delta E equal to NCV delta T from here. It's always true and to any ideal gas. By first thermal law, delta E equal to Q minus W. Delta E internal equal to NCV delta T. This is ideal gas, any process. Okay, we look at this one. Initially, the state is R here, and it can go constant volume. Okay, this way to this final state. It go to the constant pressure, go to final state. Also, it can go to adiabatic process. All these processes, the delta T is the same. Delta T is the same. The kinetic energy is the same. Okay. A change in internal energy, E internal, of a confined ideal gas depends on the change in the gas temperature only. It does not depend on what types of process produces the change in the temperature. Whatever constant volume, constant pressure, diabatic process, they get the same answer, delta E. And we're going to CV equal to 1 over N, delta E internal over delta T. This table shows that one. Monoatomic, its CV is 3R over 2. Okay? This is diatomic, CV is 5R over 2. And this polyatomic, CV is 3R. And look at this, helium, argon, they are almost the same. Diatomic, nitrogen, oxygen, they are almost the same. Polyatomic, there's ammonia and copper diode is almost the same. Molar specific heat at constant pressure. This is constant pressure, okay? Now we see this one. We put the shut constant. So whatever it extends, the pressure is the same, the constant pressure. And here you can have a heat exchange with a heat reservoir. What I do, you see there's an initial state, the constant pressure, this is the pressure, from initial to the final state, okay, the final state. Here you have a V plus delta V, T plus delta T, and so on. Now in this process, we see, for the first law of thermodynamics, Q equal to delta E internal plus W, okay? And this one, we have learned, whatever process is NCV delta T. And the work at constant pressure, we can P take it out, is P delta V. And P delta V equal to NR delta T, because PV equal to nRT. Okay. And by definition, this one, Q is delta E is NCV delta T, W is NR delta T. And by definition of heat capacity, QP equal to CP delta T plus the mass, right? And we compare these two, we get CP equal to CV plus R. This relationship is very important. It not depends on anything else, just a relationship. CV and CP. Cp is always larger than Cv. Sample. A bubble of 5.0 or more of helium is submerged at a certain depth in liquid water. When the water, and thus the helium, undergoes a temperature increase delta T of 20.0 degrees Celsius at constant pressure. The process is at constant pressure. As a result, the bubble expands. The helium is monoatomic and ideal. Question A. How much energy is added as heat to the helium during increase and expansion? We want to find the Q. Okay? This is a constant pressure pulse. So by definition, Q equal to NCP delta T. Delta T. We know delta T, 20.0 degree. Okay? We know Cp because it's monoatomic. Cp equal to Cv plus R. Cv is 2/3 R, so percent is 5R over 2. And N is 5.0 or more. We put this number, get through, this is, okay. N, this is Cp delta T. N is 5.00, 2 have 5 are 8.31, delta T 20. We get a Q. We take the three significant figures, so we get a 208 joule. Question B. What is the change delta E internal in the internal energy of the helium during the temperature increases? This is whatever is delta E is by formula is always NCV delta T. Okay, this CV is 3/2R. Okay, this is a 5, this is 20, so I put it inside, we get delta E. All right? Yeah. Take 3 digit significant data figures, you get them 3, 2, 1, 2, 5, 0. Okay. How much work W is done by the helium as it expands against the pressure of the surrounding water during the temperature increase? By the first law of thermodynamics, we know W equal to Q minus delta E. We just calculated the Q and delta E. So we put a number inside. We get the work done by the gas. Sample. A cabin of volume V is filled with air, which we consider to be an ideal diatomic gas because oxygen and nitrogen. At an initial low temperature T1. After you light a wood stove, the air temperature increases to T2. Question. What is the resulting change delta E internal in the internal energy of the air in the cabin? Not in the cabin. Okay. Now we know PV0 equals to nRT1 is original formula. Then we know P is constant when it's expansion. P is always constant at air pressure, right? And the T final is T1 plus delta T. Okay, so we put this one, P is constant, P delta V equal to NR delta T. Okay, delta T. And we combine this one, we find E initial equal to NCVTI by definition. E final equal to NCVT final. Here we have to notice that when the temperature increase, the gas expand, so some of the gas get out of this cabin. Only a limit part of it retain in the cabin. So the energy, internal energy, gas in the cabin is a little bit different from total. Is total internal energy multiply the percentage. The percentage is V0, the cabin value. This is it expanded. V0 plus V delta V is V final. Okay, so we look at this one. What the internal energy change is E F prime minus EF, and this one looks at V0. V0 equal to nRTI over P. So this is nRTI over P. This is nR delta T over P. So this one equal to nR over P cancel out. Okay, we get E final in the cabin is NCV F final. This is a T over T plus delta T. And T plus delta T equal to T final. This T final cancel out this T final. So E F prime equal to NCVTI equal to E initial. So that means the internal energy change in the cabin is 0. Degrees of freedom and molar specific heats. The equipartition of energy. We know that every kind of a molecule has certain number F of degrees of freedom, which are independent of ways in which the molecule can store energy. Each such degree of freedom has associated with it on average an energy half kT per molecule or half RT per mole. So E internal equal to 3 over 2 nRT for monatomic gas, because monatomic gas has 3 freedom. Okay, and we extend this one, which will say the internal energy for the gas, any gas, equal to 2F nRT. This is, we replace F 3 with F. Okay, F is the freedom of the gas, and the CV equal to 1 over n delta T over T. So we do this one, we find CF equal to half FR. The R is 8.31, but 4.165 F. This is energy. Now let's look at the degree of freedom. One monatomic gas, it can have only 3 freedom. Translation along X, along Y, along Z. So 3. Okay. We see diatomic atom, they have 2. So each one has 3 dimension, degree freedom. So 2 and 3. But they have things connected. They have a confinement 1. So -1 is 5. So it has freedom 5. And we look at it in other ways. We can look at its whole stuff. It can have 3 translational freedom that go with the center of mass X, Y, Z. And it can have 2 rotation around this axis, along this axis, but not along this direction. Okay, because around this rotation it doesn't have any change. So the freedom is 3 translational, 2 rotation. Look at this ammonium. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bonds. Okay. How many? 1, 2, 3, 4, 5. So 5 atoms. We have freedom 3 times 5. But they have 10 bonds. 10 bonds, only 9 is really bond. Another one is nothing. So 3.5 minus 9 gets 6. We look at it in other ways. The whole molecule can rotate, can translate. They have 3 translational freedom and 3 rotational freedom. Now, this is the degree of freedom. Okay, monoatomic, you have 3 translational. So CV equal to F is 3 R over 2. CP is 3 R over 2 plus R, 5 R over 2. Diatomic, like oxygen, it has 3 translational freedom, 2 rotational freedom, 5. So CV is 5R over 2, CP is 5R over 2 plus R, 7R over 2. Polyatomic, like CH4, it has 3 translational freedom, 3 rotational freedom, 6, F equals 6. So CV equals 6 over 2, 3R. CP is 3R plus R, 4R.
We'll use these spheres moving in a frame to simulate the equipartition of energy among gas molecules of different mass. These spheres all weigh the same and travel at a low average speed. When we add a set of lighter spheres to the frame, they travel at a higher average speed. The average kinetic energy in the motion of the lighter spheres is approximately equal to the average energy in the heavier spheres.
A quantum theory, which you can look at the energy of this gas. It can be translocation on CV to third, or you have a rotation, you get 2 or 5, or you have oscillation 2 or 7. They are the quantized. The energy is quantized. This is a hint, okay, for quantum mechanics energy.